Hello, good afternoon, sir. Good afternoon, everyone. We're here to present Group 5 project, which is a 4-bit adder subtractor. And here we're gonna show the design of experiment. And first, we have to initialize ceilings, and we can do that by initialize it again by clicking this executable file of ceilings ISC, which is also shown at the documentation that we provided. Secondly, we are going to add a new project. You can rename it anything, and let's try test the design. And then we have to follow what is written at the document for the parameters. Click next, and we have to add a new source for our 4-bit adder subtractor. So do that by right clicking this one and adding new source and choosing Verilog module. We're gonna rename ours 4-bit adder add sub.
Verilog module.
Oh,
Get
Verilog. Iba ba yung nilaki ko?
previous.
Yeah, Verilog module. 4-bit add sub. Then we're gonna define this later, the inputs and outputs. You can define it here too, but we're gonna define it at the code. And we are left with this, and we provided the code at the document. Right here.
One for the full adder, one for the
First,
4-bit adder subtractor.
we need the full adder, so we have to create another source for the full adder. Full adder. And here we're gonna use what is provided, what code is provided, and we're gonna copy paste it here. And then for the 4-bit add sub, we're gonna use this code. So what this code does is it's gonna use the full adder to be implemented in the 4-bit adder subtractor. So it's gonna use the code inside here to be implemented here. After you doing all that, we have to create a test bench to verify the syntax of our document. We're gonna use the code that's already done for ease of access. So this is the full adder that we showed earlier. There are four full adders here because we're gonna use four of them since it's 4-bit. Then after doing that, we have to make a test bench to verify. So we can do that by right clicking again, new source, and add a Verilog test fixture. You can rename it anything you want. And then it will show here, and here is our test bench. And basically what you need to do here is you have to create parameters in order to simulate every value for the uh, for the 4-bit adder subtractor. In this case, we also provided a code for the test bench. Which is here. Yeah, this is one way. This is one way, but this is also another way that we show here. And then after implementing those, and we can press behavioral check syntax to check if the code works. And if it checks in green, then you can simulate the behavioral model right away. Wait a second, simulate behavioral model field. Sorry for the technicalities. There was another there was another iSIM already running at the background, so we're gonna check behavioral checks syntax again. Then simulate the behavioral model. Just wait for it to launch. If there
Sige,
was
rerun mo.
an error, you have to rerun the syntax. Then simulate behavior model.
Nirun mo. Yan.
And
Yan.
here we go. And we just saved our code again, and we simulated it again. And here is the full waveform. It can be viewed by using the zoom to full view. Let's change this. So this is the A and B. This is the bits that we're gonna add, and this is the sum, and this is the carry. Kaya naman. Explain nyo yung ano ito.
As we zoom in into to the waveform, let's focus on a single time interval. So as we can see in, for example, that one, the input for A is 0, but the input for B is 001, which indicates decimal equivalent of 1. So the operation that has been conducted here is pause. I-pause mo muna, bro.
Go.
Uh,
Uh,
so for this time interval, as you can see, the two inputs have the respective values. For A, there is 0000 indicating an equivalent value in equivalent value of 0 in decimal, while B, it contains 0001, which indicates a value equivalent to decimal 1. So as for this time interval, as we can see, the signal for C is low, 0, which indicates that the operation that we will perform on the time interval is addition, arithmetic addition. So as we can see, if we add A to B, which is 0 plus 1, it will result to a sum of 1. So the sum shows 0001. So that's it. That's an example of it.
go.
So as you can see on the screen, so A is 0011. It means it's 3, and B is 0010. It's 2. So C is 1. So it means we will use the subtraction. So the sum will be 3 minus 2 is equals to 1. So that's it for the subtraction.
Thank you. That's all.
Okay. So for the for the viewing of the RTL schematic, we will go to the implementation view. Then under the implementation view, under the process, there's what we call synthesize XST. Then under it, there is an option called view RTL schematic. So we double click onto it. And as it loads, it will pop up a window that will verify us the option on how to view the schematic, whether it will be on a top view or a customized one. So for this demonstration, we will choose the top view, top level block of the schematic. So let's wait for the process to finish. So we will start with the top level block. Or we can do that. So as we open this, as we click that schematic, this is this is what we will get, the RTL schematic of the HDL code that we generated in our Verilog module. So if you want to see more the inner workings or the composition of the component, you can right click it to view the inner block. So this is what happens. This is what happens when you show it. I'll further explain. I'll further explain the scheme. So the schematic composes of four XOR gates. The reason behind that is that it is for the purpose of B signal, so that we can implement a two's complement onto it. While as we can see, there's only one full adder that is inside the block. The reason behind that is that we used buses in our code. So if we use buses, it optimizes our schematic to use a minimal number of components. In this case, it's the full adder. So we only use one full adder since we've implemented buses into our input signals. So that's it.